Thank you. So my name is Jonathan Churchill, for people who don't know me, which is probably almost anybody apart from the people who turned up last week. And that's because up until 3 years ago, the network was something I knew pretty much nothing about. So it's been a kind of a crash course as JASMIN. So I now run the JASMIN infrastructure. We'll talk a little bit about the road that we went from 3 years ago and some of the mistakes we made and hopefully where the future is going now. So I work in the scientific computing department. So that's Hartree Centre is part of that, if anybody's come across that. JASMIN's purpose. So JASMIN is a data analysis platform. People often get confused between JASMIN being, because we use a lot of high-performance computing technologies, people think that it is a high-performance computer. It's actually not. So we are data-heavy and compute-light. So we store a lot of stuff, but we need to access it very fast as well. So part of the archive, and I'll talk about the size of the infrastructure in a second, is CEDA is the Centre for Environmental Data Archive. So there's about 1.3 petabytes of data. So that can be satellite data, it can be landslip, pretty much anything in the environmental sciences. It's a curated archive, so there's some metadata that goes with it. That's not part of my team, that's to do with CEDA. So I should point out this project is a joint project between the Scientific Computing and the Rutherford Appleton Space Science Department. So it's a cross-disciplinary thing as well. So then we do computing. So we don't actually do compute. So this little image that we're looking at, excuse me, here is something that would have been generated on a big supercomputer. We don't do supercomputing. What we do is we analyze the outputs from the supercomputers. So those will be, as it says, the high spatial temporal resolution. So things will be like the next generation of weather simulations. So the things that the Met Office is installing their computer for now, that kind of resolution, that kind of accuracy, we're trying to run simulations on that. We're trying to analyze the data from those. And then for people who are bringing in their own data sets, so instead of storing them in a spreadsheet on their desktop, they can bring their data into JASMIN, fire up some VMs, which we'll talk about a bit in a second, generate their own data, download some data from satellites, analyze it, share it with their friends and colleagues. And the thing that's driving JASMIN is just the size and the complexity of what's possible now. So if you look at, let's see if this actually works. So things like satellite data, the Sentinel missions are capable of, which got launched, the first one was last year, as a gigabit a second download. Okay, and that's just one satellite. You've got the complexity of things that we're able to do now in simulation. So JASMIN holds about 60% of the data that was used to go into the latest IPCC climate change report. And a lot of that data and those simulations is based on increasingly complex models. So here we're talking about clouds, which there's a lot of discussion about, but rainfall, aerosols in the atmosphere, how that bounces the sun. And then in addition, because we have these massive supercomputers, we can also run these huge ensembles. So if anybody's into that, that's really what the IPCC report is, running masses of simulations with slightly different models and slightly different input data sets to get the best view of what's likely to happen to the climate, this thing here. So this is JASMIN. JASMIN 1 is on the left. JASMIN 2 is on the right. We're just installing JASMIN Phase 3. So we have, at the minute, 16 petabytes of high-performance storage, 250 gigabytes a second. That puts it probably in one of the top 10 systems for I/O in the world. But the problem is that nobody knows how to measure I/O, so there is no known defined benchmark for that. But that's based on some papers and some work. But you can see that although we have a lot of computing at 4,000 cores, that's like nothing in supercomputing terms. But we use that to suck the data off, compare and contrast. But as you'll see in a second, the storage that we use is not cheap. It's a parallel file system, and we don't want to blow that away with constraining it with the network. And it's the network that's a primary focus of this talk. So we have a completely non-blocking network capable of doing 3 terabits a second. We've benchmarked about half of the storage at 140 gigabytes a second, and that's over a terabit a second. And then we also have some cloud hosting capabilities. So this is to address all of NERC sciences. So this JASMIN is funded by the Natural Environment Research Council, and initially it was climate change and Earth observation, so satellite data. But now increasingly it's going into everything they do with NERC. So that includes things like environmental genomics, studies of bugs in the environment, landslip data, all kinds of stuff that's going in. And to do that, obviously that data is coming in from lots of different places, and so we have some lovely links from our colleagues at Janet. So we have dedicated links up to Archer and Hector up in Edinburgh, down to the Met Office in Exeter, up to Leeds and other partner sites. This is KNMI over in Holland. We're also sucking in data from DKRZ in Germany and places in Australia and the US. So a lot of the things that's driving our networking complexity to some extent is the storage system of choice. So we use Panasas. Hands up anybody who's ever heard of Panasas before. Hands down if you were here last week. So not very many. If you talk about parallel file systems, GPFS and Lustre come up a lot. So I think the CRIC thing that you were just talking about, they use a GPFS system. But there are issues. So there's only, to manage this whole infrastructure, there's me and one other person. So everything that we do is generated for ease of use and ease of management. Panasas wins hands down on that. So that's the end of the Panasas thing. If you do want a parallel file system and you've got no people, please talk to Panasas. So the Panasas system comes as these blocks of blades. It's a bladed architecture. Each blade has 2 drives in it. The latest generations have got 6 terabytes that we're installing. 2 by 6 terabytes and an SSD. But each one of these blades is a computer on the network, so it has an IP address. So I've got 11 blades in a chassis. I've got 200 and something odd chassis. That's thousands of IP addresses. We started off thinking, oh, well, this is really easy, right? We'll just do this in a lovely flat level 2, layer 2, and we'll do that in a /21 network. Everything's good. And as I'll show in a minute, of course, we got burnt by that very quickly. So you pay money with this, but actually you don't pay. People talk about Lustre and GPFS as being cheaper and Panasas being really expensive. Actually, when we did the cost comparison, the Panasas system actually works out cheaper. And given that it's only one management console for 16 petabytes, that's a big saving in people. So 3 years ago, my line manager came to me and said, hey John, wouldn't you like to look after 4 petabytes of storage? It's only Panasas, it's one management console, how hard can that be? And at the time I thought, yeah, that's really easy because this was the network we had. These were nodal switches, so unfortunately they've gone out of business now, but these are 40 port switches, so 440s, 160 ports, 4.5 petabytes and about a couple of hundred computing cores, so nothing very much. You know, we did have VMware, we had a HPC cluster formed from that, but really not very much. And then a year later they said, could you add a few more compute cores and a bit more storage? This is the inevitable growth. And I went, yeah, well, I kind of like run out of ports. Can you buy me a few more switches? So we spent some time with Nodal and we came up with this lovely thing. This is all still layer 2 only. And we got up another 80 ports. That was really cool. And that worked really well. And then about 2 years ago, they came back and they said, well, we now need 15 petabytes of storage, several thousand cores with this cloud capability as well, and we need to add more of these optical links. So we needed a network that kind of sat in the middle. And you can see that you're instantly adding hundreds of ports, and these are all at 10 gigabit. So 300 and odd ports for the storage. We got 4 VMware clusters for different parts. And as anybody who's done any virtualization knows, that's not actually that easy. And then in addition, we do have a standard HPC cluster. As I'll talk about in a second, we're not aiming to be the biggest in the world. We're just aiming to provide an incubator service for people who want to run MPI jobs. This is a parallel processing job so that they can then step up to the likes of Archer and Hector. And that's pretty big as well. And it, yeah. So if there are campus managers out here, this is my campus. This because I kind of think about this because JASMIN contains everything in it, because it's got virtualization, it's got FTP servers, it's got login servers, it's got pretty much any kind of VM you could think in there. It's got HPC, it's got high performance storage, it's got a SAN, it's got everything in there. But my campus is only 30 meters by 20, which helps me a bit because it means I don't have to go to BT to procure some network links, but it does still cause a massive headache. So trying to design a network for going into the future. So after the JASMIN 1, JASMIN 2 and 3 that we're in now, there's an expansion plan that takes us out to 2020, which I'll talk about in the last slide. So our criteria was non-blocking. We've just paid a lot of money for a parallel file system. I don't want to then constrain it by the network. Low latency, so we want to be able to do sub 20 microseconds MPI. We were at over 100 microseconds with the previous JASMIN 1. Small latency spread. This is driven by the number of people. I don't want to have to manage an InfiniBand network and a fiber SAN as well as a standard Ethernet network. I want to do it all in one go. I've got the original spec for JASMIN 2 was that range of ports, but actually we've blown through that, and I'll talk about that in a second. And because we knew that we were going to want to expand to more ports. So we wanted something that we would be able to basically be ahead of the game, so not get stuck in this thing where every year comes by, so they need to do another forklift upgrade to completely reconfigure the network to get more ports into it. Again, we don't have many people, and yeah, of course it would have to be cheap. And then later on we had this little problem because Nodal went out of business, so we had to replace that network as well. So along the way, we were worrying about the cost of this thing, and I only mentioned this in passing, but fiber connection between 2 points on the network, if you do it with fiber, you're talking about 400 to 600 quid per connection. So with the number of connections we're talking about, you can spend £500,000 on cabling costs alone. In the end, we got the JASMIN 2 network in at around about £500,000, including the cabling. We had quotes that went up all the way to beyond 1.5 million. And that's the reason for the bloat is because most people kind of specify this kind of switch. It's a fairly standard thing. That's a Dell 4810, 48 ports on the front with 440s coming out. If you want to do non-blocking, you can only use 16 of those ports. So it instantly becomes really expensive. So this is what we ended up with. I believe this is fairly unique. These switches are from Mellanox, and they have 48 ports on the front and 12 48s coming out the back, which you can drive full rate. So all the data I pump in the front, I can uplink without blocking it. Everybody else, as I said, you have to drop some ports. This was the original design for JASMIN 2, which took us to 768 ports, but it was fairly clear from that we were going to instantly blow through that. So actually we've done 12 switches up here, and I wasn't going to draw the diagram with 12 switches in because that's just a nightmare. It looks worse than it actually is on paper. When you go to the back of the rack, here is our 12 spine switches, these things over here, and each one of these orange things here is a 40 gigabit fiber. There are currently 204, there's about to be 230 of those 4 gig fibers, and that's where the 3 terabit networking comes from. But each one of those, so you've got 12 stacks here, each of the leaf switches has got one cable that goes to each one of those. So it's actually not that bad to cable. It looks worse than it actually is, because you're just running a bundle of 12 40 gig fibers. So this will get us up to 1,728 ports, but as I'll talk about in a second, we're probably liable to rip through that sometime between now and 2020. So we do need an expansion plan, and I've got some ideas on that. Yeah, we actually achieved our 10 microsecond latency, much better than the 20 that we thought we were going to get, and it was kind of cheapish. Well, it actually, for a change, you actually got you got your cake and you got to eat it. So we actually got the fastest solution, and it was the cheapest one as well. Now, I don't know whether that was because Mellanox were doing us a good deal, but who knows. And to prove that it works, so this is pinging between a couple of hosts either side bouncing around. So I don't know if you can actually read that from the back, but that's 0.2 milliseconds of ping. That's not MPI latency, by the way. But you do get this kind of odd behavior where you get you're bouncing around between the ECMP hops in the network. So for some users that looks a bit confusing. And to prove the ECMP works, this is at the minute we have up until Tuesday next week, we have a 40 gig pipe coming out of JASMIN 1 and then going into JASMIN 2. This is one of the leaf switches in JASMIN 2, and here is our 12 spines. And you can see I've got a 5 gigabit stream here, and it's being equally chopped up between all of the links. So there's a bunch of advantages. However, with this kind of scale, brings some issues. There's a lot of IPs. There are literally thousands of IPs, and you need to manage them. There are a lot of subnets, hundreds of subnets, and the VLANs and the cabling and the monitoring is starting to become a real overhead. So one of the things I was hoping to get from today is SDN. Ideally, we need something to help us manage this complexity. We're doing okay, but I'm not saying it's great. And it's also routed through a layer network. So there's a lot of things that don't really comprehend this. So the complexity is one of those. If I do show IP route on any one of those leaf switches, literally the number of routes just goes straight off the bottom of the page. So trying to pick out what is your routing is a problem. There's no layer 2 between any of these switches, and that breaks some of the assumptions that vendors like VMware assume. So they make an assumption that your SAN is on a layer 2 network. You can make it work on layer 3, and we have done so. But there's a bunch of assumptions in the way that the infrastructure is set up, which means that it complicates the DHCP relay, and it forces you to use VXLAN. And also you get this trace route thing that I was talking about earlier from the pings, that the users see something which is a lot more complex than they would otherwise think it is. So just digging into that for a bit, one of the reasons for the IP and the subnet management is here is 12 cables going from this is 17, I think, from one spine switch to the leaf switches. Each one of those has a /30 network on it. So there's a /30 network with a gateway and a broadcast address for every single one of those cables, all 230 of those. And you need to make sure they don't clash, because otherwise the OSPF routing is going to screw up. And then when you look at the individual switches, of course, they're completely isolated. So each one of the VLANs and the subnets on the switches has got its own gateway and broadcast address, and there's a subnet on here. The subnets we use range from anywhere from /26s to /24s to break up the IP space. So that's a headache managing that as well. So when you look at our IP plan, and this is just a section of it, it just goes off the end of the list. There's a lot of switches that need monitoring, and this kind of leads to the Nagios bloat. We realized fairly early on in JASMIN 2 that we ran a Nagios infrastructure for our existing stuff, so we run a bunch of HPC clusters as well. And we suddenly realized that JASMIN was actually consuming well over half of all the tests that we were running, and we weren't monitoring all the things that we needed to do. So just monitoring infrastructure like this is a problem. Thousands of IPs. So, actually typing those into IP plan is a pain. You need some kind of automation to do that. And monitoring it is a problem as well. So we started off with this lovely thing with Cacti, where you kind of, I don't know if anybody's done this hierarchical stuff, but you click on one of these blobs and it opens up and you get another picture. So in this case, there's a 40 gig data stream going from our old JASMIN 1 into JASMIN 2 here. And you click on this one, and this gives you the picture that I showed you before, with the spine and the ECMP going off to the spines, and then actually you click on one of the spines and that takes you to all the leaves that it's connected to. But it takes a fair whack to actually configure that but you do need to see where all the data's going. So, what do you do with it? So that brings us to VXLAN. So this is one of my leaf switches, and behind each one of the leaf switches are 24 servers. One of the things we do in JASMIN is we don't have a dedicated bunch of hypervisor servers. So we have one set of servers that can provide a pool that can either be, we can swap them between being an HPC server and being a virtualization server. So we can just redeploy them on as we like. And that means that we never end up having a bunch of infrastructure standing by. So, if we're not using the full complexity of if we don't have enough VMs that are spooling up at the time, we can just flip it over into the Lotus HPC cluster, and that will just improve the throughput. And given that we just passed our 3 millionth job in two and a bit years on Lotus a couple of months ago, every job counts. So so the problem is all the subnets are contained in this switch that are connected to 24 servers. Well, I want to do any maintenance, it's a single point. I can't sweep all these VMs from this switch over to these hosts, even if it's free, because the IP address on the VMs on here are locked down to the subnet that's on here. So if I move the VM from here to here, it has to be on a different subnet to make the layer 3 work. So you need VXLAN to do this. And kind of going into this, I think VXLAN people have been talking about it for maybe 18 months, maybe 2 years before we went into this. So you kind of think that maybe people had knocked out the bugs from it. I think it's not quite true. So we're trying to use the multicast version of VXLAN, and that's the one that comes with the EXXi. At the time we bought our licenses, we couldn't afford the NSX, which uses unicast VXLAN, and probably that's better supported. So, if we had our day again, maybe we'd make a different choice. So to get this to work, you need PIM in the switches, and the PIM implementations are not great. We did an upgrade to fix something, and the switches that we hadn't upgraded were the ones that crashed in the infrastructure, not the ones that we had upgraded. So this is not great. It also comes with a 50 byte overhead, so this is a bit of a VMware snafu. So in our infrastructure, in order to mount the Panasas Storage, you need jumbo frame. Well, it's desirable to have jumbo frames enabled because it gets you about another 10-15% throughput. But if you take a VM and you set MTU equals 9,000, it won't work when you try and pump it through VXLAN because of the 50 byte overhead, and VMware won't allow you to do anything more than exactly 9,000 in their virtual switches. Okay, cool, I'm on the last one. So JASMIN expansion, what are we going to do? We've got, the project tells me they need to go to 30 to 80 petabytes on disk by 2020, but there's a demand for 300 petabytes. Yeah. So we're probably looking at 2 to 3 K 10 gig ports, and that's obviously going to rip through the 1600 port limit that we're on here. So, there are a couple of ways that we could go, but the nice thing about the route that we've adopted is it's a standards-based approach. So, theoretically we can tap in any switch. So this just happens to be a Dell Z9500, which has got 144 40 gig ports. We could, in principle, stitch one of those in, replace the 36 port switches we've got here. We could do things with 100 gigabit fabric that's just coming out by now. So there's lots of things that we can actually play with, but because it's all standards, theoretically we can mix and match. But all of that is just going to get worse. We need automation, and maybe SDN can help us with that, which is good because that's what some of we're going to talk about today. Any questions? Do I have time for questions?
Yep. We've got time for one question. Anybody want to ask Jonathan something about the JASMIN infrastructure? Okay. Well, thank you very much.
Cool. Okay.
Thank you.